All right, so this is the first of two lessons on looking at a specific type of problem, which is what we call a related rate problem, or just a rate problem. And the idea of using derivatives to figure out rates is fairly straightforward. I mean, a derivative is essentially a rate, the change in y over the change in x. But a related rate problem is where we have some sort of scenario where the change in one thing affects the change in something else. You have this system, in essence, where there's different things changing and they're related to one another. And if we can figure out how these different parameters are related to one another, then we can use derivatives to see how the change in one affects the change in the other. That's it. I have a couple problems I'll look through for this lesson. And for each of these, I'm going to use these suggestions at the start here as to how to approach these problems. Although there is a wide variety of problems, and we'll look at a variety over the course of two lessons. So there's 4 points here, these suggestions about how to solve a rate problem like this. And I'll go through these one at a time. So the first suggestion is to visualize the change as a diagram and clearly label the rates we're given and the rates we're trying to find. So essentially a well-labeled diagram. So let's look at this first problem. A ladder that is 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? Okay, it's a big sentence. We'll probably read this more than once, but let's first start with a visualization. We have a ladder resting against the wall. So let's draw some ground here. Here's my wall, and here's my ladder, blue ladder. Okay, and the ladder is 10 feet. And I'm going to assume, they say it's a vertical wall, so actually I don't have to assume. This is a right angle right here. So I have a right triangle. Okay, so the ladder is a constant. And let's go back to what the question says. The bottom of the ladder slides away from the wall at a rate of 1 foot per second. So the bottom of the ladder is sliding this way. So I'm going to draw this arrow to make it clear that that distance at the bottom, the base of this right triangle, is expanding. And now that is not a constant. So I mean, the ladder is always 10 feet. It's moving, but its length of it is always 10 feet. This distance at the bottom is changing, so I'll call it x. But we also know, actually I'll leave that for now. I'll just call that x. And therefore, if the bottom is moving out, that means if I look at the top of the ladder, this distance must be shrinking. Just makes sense. As the bottom of if we know the bottom of the ladder is sliding out, we know the top of the ladder must be sliding down. And I'll call that distance y. Again, that distance there is a variable. It's changing. The only thing that's constant in this relationship here is the hypotenuse of this right triangle, the length of the ladder. Okay, what other information does it give us? It says right here, not only is the bottom of the ladder sliding away, it slides away at a rate of 1 foot per second. So this x is changing. It's getting larger at a rate of 1 foot per second. I can express that rate of 1 foot per second as a derivative. I can say the change in x over the change in time equals 1. I'll put foot per second. Most importantly, just it's 1, and it's a positive number because it's getting larger. If we said that the bottom of the ladder was being pushed towards the wall at the same rate, then this derivative dx dt would be -1 because the change in x is shrinking. Or I should say x is shrinking, so the change in x is a negative value. And so back to the question, how fast is the top of the ladder sliding down the wall? So I'm trying to find the change in y. So I can express what we're trying to figure out as a derivative. I can say dy dt equals, we don't know, that's what we're trying to find. In fact, I'll actually rewrite this and just be more explicit. And so we want to find dy dt. But I will say, just that alone is not enough because the change, if I just say find dy dt, that implies that as the ladder slides out, the top of the ladder is sliding down at a constant rate. And that's a bad assumption. That may be the case, but actually quite often it's not the case. And so don't assume just because the bottom of the ladder is sliding out at a constant rate that the top must also be. It depends on this relationship. And so notice the last thing it says is not only find how fast the top of the ladder is sliding down the wall, but at the instant when the bottom of the ladder is 6 feet from the wall. So more specifically, I'm trying to find dy dt. I want to find the change in height over time. but specifically when x equals 6. When that distance at the bottom is 6 feet. And so now notice, if I look back at what the question says, a 10-foot ladder rests against the wall. If the bottom of the ladder slides away at a rate of 1 foot per second, how fast is the top of the ladder sliding down the instant the bottom of the ladder is 6 feet from the wall? All of that now, which I had to read through a few times, has now been visualized on this diagram. And that's a challenging task. Please don't assume that this first suggestion of visualizing the change as a diagram, requires artistic ability and is kind of superfluous or is not really, is kind of trivial. It's a big task. Okay, I've now visualized what's happening here. Okay, what's the second suggestion? Determine an equation that shows the relationship between all the variables. As it says, this may involve combining different equations. So I now know what I'm trying to find. So now how can I express this change between x and y and the length of the ladder mathematically? Well, sometimes this is extremely challenging, and it requires looking at a combination of functions and putting them together. In this case, I hope it's not too challenging to see how x, y, and 10 are all related. It's a right triangle. So I can relate them together with the Pythagorean theorem. So I can say x squared plus y squared equals 10 squared. There we go. In this case, as soon as we know there's a right triangle, I don't think it was a big task to figure out the relationship between x and y in this case. They must be related based by the Pythagorean theorem. All right, so next, differentiate this equation with respect to time. Usually this will involve implicit differentiation. So I want to find d dt of everything, because I'm trying to find how x and y are changing over time. And I know I'm trying to find how it's changing over time, because first of all, if you think about a speed, how fast is something changing? That's usually centimeters per second, meters per second, feet per second, something over time. And I'll say as well, in general, with probably every problem you'll see with these related rate problems, we're trying to find how various parameters are changing over time. So I can't, off the top of my head, I can't actually think of an example in which you won't be differentiating everything with respect to t for time. So this equation here, I want to differentiate everything with respect to time. So d dt of x squared plus d dt of y squared equals d dt of 10 squared, or 100. I'll just say 100. It's a pretty nice number. All right, so now keep in mind, what am I differentiating here? I'm differentiating with respect to time. And so if x, y, and time had nothing to do with one another, this derivative would be 0. Same thing for this. This derivative would be 0, because we're not differentiating with respect to x or y. We're differentiating with respect to t. But x, y are related to one another, and they're all changing. They're all related to time. They're all changing based on the time. And so I have to use the chain rule and essentially implicit differentiation here. And so let's look at this first example. So I'm going to use a chain rule here. And so my outside function is the quadratic part. The inside function is x, which itself is a function of time. That's it. Differentiate the outside function. You got 2 times x times the derivative of the inside function, which I can just write as dx dt. Which, keep in mind, we know dx dt, highlighted in yellow over there, is 1. The change in x over time is a constant. I'd say at the beginning of the question, it's moving out from the wall at a rate of 1 foot per second. Okay, similarly, use a chain rule for this. Very, very similar. Differentiate the outside function, that's the quadratic part, that's 2 times y, times the derivative of the inside function, which is dy dt. That's what we're trying to figure out, right? If I look back at the question, I'm trying to find dy dt when x equals 6. That's it. On the right-hand side, the derivative of 100 with respect to anything is going to be 0. 100 is a constant. Okay, so we're trying to find dy dt. So let's isolate dy dt. In this case, it's pretty straightforward. To isolate dy dt, I get negative 2x times dx dt all over 2y. Well, I might as well clean that up a bit, cancel out the 2's. So I get negative x times dx dt over y. Oh, I've highlighted these the wrong color. That should be yellow. So at this point, I know what dx dt is. I am trying to find dy dt, and I have my derivative right here, kind of simplified. So what do I do then? Well, to actually find my derivative, I need to figure it a little bit more, because dx dt is 1. X is the distance across the bottom. Well, notice if I go back to what I'm trying to find dy dt when x equals 6. So that x right there, I know, is 6. The only thing I don't know yet is this y at the bottom in the denominator. And that represents the height of the ladder from the wall the instant the bottom of the ladder is 6 feet from the wall. So I'm just about done. I need to figure out the value of this y right here. And again, that represents the height of the ladder the instant the bottom of the ladder is 6 feet from the wall. The good thing is I can figure that out quite easily using, again, the Pythagorean theorem. So when x equals 6, I can say that x squared plus y squared equals 10 squared always. So in this case, 6 squared plus y squared equals 10 squared, which means y squared must be equal to 100 to take away 6 squared, which is 64. And so y must be the square root of 64, or just 8. Again, we're dealing with distances, so it's only a positive value. So all I've done is done a bit of grade 8 math to figure out, okay, the instant the bottom of the ladder is 6 feet from the wall, the height of the ladder at that instant is 8 feet. And so now I can actually answer this question. So let's find dy dt. It's going to equal negative 6 times 1 over 8. Again, that negative 6, that's the instant we're trying to find when the, what am I trying to say? I'm tired of talking about this question. That's going back up here. Right, we're trying to find dy dt, the instant that the bottom of the ladder is 6 feet from the wall. All along we've known dx dt is 1, and I've just figured out at that instant the bottom of the ladder is 8. So it's negative 6 over 8, which reduces to negative 3 over 4. Now what are the units? Look at my derivative right here, dy dt. The units of y are in feet, so feet per, and the units of time from the question are in seconds. All right, so with that said, keep in mind this question. I guess I skipped this step here. Well, I didn't skip it. I forgot to mention it, but that's what I did at the end. My last thing I did is I used the values that we were given in the question to evaluate the required rate. That's it. Once you get to the derivative, it's probably fairly clear what we have to do. Even though it may not always be easy to actually do it, but it's probably fairly clear trying to isolate a particular derivative. So before we go on to the last and second question of this lesson, keep in mind in this case, I had a relationship between height and the base of this triangle. And when one changed, the other changed. And so I have to find first the relationship between them, in this case the Pythagorean theorem, differentiate, and then figure out at that instant, the instant in this case the bottom of the ladder was 6 feet, how quickly the top of the ladder was changing. And as well, notice my answer was a negative number, which made complete sense. If that was a positive number, I know I made a mistake. I know it must be negative because I can just tell by looking at this diagram that y is getting smaller, which means the change in y must be a negative value. All right, let's look at one different example. And again, I'll follow these same steps. So, a hot air balloon is rising straight up from a level field and is tracked by a rangefinder 500 feet from the liftoff point. At the moment, the rangefinder's elevation is 45 degrees. The angle is increasing at a rate of 8 degrees per minute. How fast is the balloon rising at that moment? Like before, you're probably for sure going to have to read this a few times. And let's now start to recreate an image here. So a hot air balloon is rising straight up from a level field. So I'm going to draw a level field, straight line. And I have a hot air balloon, so we're going straight up. It's rising, so I'll draw this here. And here's, I'm too lazy to draw. Maybe I'll draw a little balloon. There we go, a little hot air balloon. There we go. Very important. All right. That's going up. And so I'm just going to call that y right now, that distance. What else does it say here? It's being tracked by a rangefinder 500 feet from the liftoff point. So this blue dot I put in the right here, I'll highlight, that was a sort of liftoff point, I guess. So 500 feet from it, to the left or the right, I'll draw it to the left, I'll put right here. That's the rangefinder. And I know the distance between these points is 500 feet.